Hi everyone, myself Orkojyoti, and today let's solve a beautiful question from LeetCode, that is question number 3372. And in this question, we are going to solve uh, a question that is regarding graphs. So it will help you to have an in-depth practice of graphs and logic building in this data structure. So the question is, it is a first of all medium level question, so that is not too easy and not too hard. And this question is maximize the number of target nodes after connecting trees. Part 1. There is a part 2 of the same question, a little bit of changes here and there. So to solve the part 2 also, you need to very well understand the part 1. Uh, if I talk about this problem, I was giving the contest, and then I actually encountered this question, weekly contest of LeetCode, and uh, I couldn't actually able to solve it. It took me a very long time to analyze the question, because the question seems to be very large at first, but once you understand it, becomes pretty easy. So the question tells that, suppose you have given two graphs, two trees. The first one is, I'm taking an example that is given. This is suppose tree 1, and the second one is like this. I'm not too fast in drawing, so please bear with me. So this is suppose tree 2, and here we have used zero based indexing, right? So this is 0, 1, 2, 3, 4. The 3 is a bit out of the circle, so let's fix it. 3, 4. Okay, then 0, 1, 2, 3, 4. 0, 1, 2, 3, 4, 5, 6, 7. So first of all, let's understand the question. The question is, find the maximum number of nodes, like we have to make an array for tree 1. Let's make an array for tree 1. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. The index actually shows the corresponding nodes here, and the question says that how many target nodes are, like, this is not odd or even part, this is maximum possible number of nodes. First tree, if you connected them. Okay, so you will be given a k, and for this one the k is 2, and how many nodes are actually connected to this one for the number of edges is less than or equals to k. Like for 0, let's count for 0 for this node. If we will count for this node, 0, this node is a target to itself, because for traversing from 0 to 0, we are actually encountering no edges. No edges means 0 edges, and 0 is lesser than or equals to 2. So for this one, self is 1. I have written 1 for it, and 1 for, I will count this node. I will count this node because only one edge. We have encountered only one edge to traverse from 0 to 1. So one node as well for 0 to 2, one node as well for 2 to 3. For 0 to 3, we have counted two edges. Two edges we have encountered. So we will count 3 as well. We will count 4 as well, because only two edges are encountered. And now you need to connect this one to one of the nodes in tree 2 such that if I will connect this to the 0th node to the node 2 of the tree 2, so and the k is equals to 2. So now if I will count how many target nodes I can choose from here, like k is equals to 2, right? 1. So I can, this one I can take is equals to 2, 1, 2. This one I can take, and I can take, okay, let's analyze 0, 2, 2 and 3, right? Okay, the drawing is a bit complex drawn by me. It should be like this and it should be like this. So if I connect this node to the node 2, then I will get this node, I will get this node because only 2 edges. I will get this node because only 2 edges. I can't take this one because here are 1, 2, 3 edges are coming, right? So I can take only this 2. For 0, how many target nodes we are going to get from tree 1 and tree 2? From tree 1 I can get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 nodes. And how many from tree 2? So for 2 I am getting only, if I will connect 2, I am getting only 3 nodes. That is for k equals to 2. But now I need to connect this 0 to each and every other node to find the maximum number of nodes that are connected to 0 if I connect it to every other node in tree 2, such that the number of edges that we encounter in traversing from this node to the target node of tree 2 is lesser than or equals to 2. So what approach can I think? We have understood the question. So let's rub it a little bit. What can I do? Okay, let's k is equals to 2, right? So let's rub these things. Let's clean this, and we are done. We are good to go now. 7. This is 2. This 3. This is 0. I think I need to draw it another time. Okay, no, it's fine. I think it is quite understandable, right? So if I will check, so what can I do here? So what will be my approach to this question? how I'm going to approach this. So if I talk about this, what should be a primitive or brute force or naive solution that just clicks in my mind. So here we are going up to k, right? Up to kth level. Think of it as a level, right? We are going up to kth level. So as we are going up to kth level only, we don't need to traverse the whole tree from the target node. For the first time, it is 0 here, right? So let's think for k. Suppose, for example, we got a very huge tree, like very huge, it's right. If we got a very huge tree and we get k is equals to 1, then we just have to traverse up to level 1, right, to get the target nodes. So here my intuition should be I should be using breadth first search, because we are going breadth wise or level wise. If we have used depth first search, then the problem will be solved, but the time complexity will be very high, because for depth first search, the word depth is coming, right? For depth first search, we are going to each and every depth, each and every depth. Then we are coming back and going to the depth. So just for kth level, we are going to all the levels to count how many target nodes are present. So that is not so good to do. That will be not a good thinking. So let's go for breadth first search, and I need to count. First of all, I'm just doing it for tree 1. Let's divide the question so that you will understand it pretty well. Let's make a division mark here. First of all, just forget about the tree 2. Just think about the tree 1. So if I think about the tree 1 only, if I am doing breadth first search here, and I'm starting from here, this is level 0, this is level 1, this is level 2. I will go up to level 2 in breadth first search, and if just you in breadth first search, just you add it to the answer list, right? Answer dot add that thing that is popped out from the queue, right? Use queue in this, and stacking depth first search. The thing that is popped out, you just add it. You just count how many nodes are present when you are in this node. Check its current level. If the level is lesser than or equals to k, then add +1 to count. Take a count variable that initially has count is equals to 0, and add +1 to count. And like that wise, when you are traversing each and every level, check that if the current level is lesser than or equals to k, and if it is lesser than or equals to k, then add it to count. By doing this, you will find how many target nodes are present for the 0th node in tree 1. Now for tree 2, likewise you can get for tree node 1, node 2, node 3, node 4. Likewise, you can do a BFS in a whole tree traversal in each and every node, and for each and every node you are going BFS, right? So what will be the time complexity? Let's not talk about the time complexity right now. We will check about the time complexity later on. For tree 2, if I talk about tree 2, what should be my approach? I have to found that how many. First of all, I need to check from 0th node. I need to connect it to which node in this, so that I will get the maximum number of target nodes. So let's think it in this way. If I connect the 0th node from T1 to 7, then if I need to go from 0 to the other nodes, the level should be here from one edge is taken by this one, right? From 0 to 7, this edge is already considered, as we are imaginarily connecting it of tree 1, 0 node of tree 1. So one edge is already used by that. So from 0 to 7, one edge is already used. So for this one, let's calculate for the node 7 that how many of the nodes are having edges between them from the 7th node, that is k minus 1. For this one, consider k minus 1, not k, because one node, one edge is already taken by from 0 to 7. So now if I talk about k minus 1, for 7, count how many nodes are present in edges lesser than or equals to k minus 1. That is, here it should be 1, right? K is 2 for this example. How many nodes are there in edge 1? There is, this one will be considered because edge 0, this one will be considered edge 1, not more than that. So you need to check for each and every node. Every time you traverse for 0, you need to check each and every node, and which one will give you the maximum number of target nodes, you will add it to the node of tree 1, right? But if we go by this approach, for each node you are traversing for your you will traverse each and every node of tree 1. So that is, let's consider tree 1 has n nodes and tree 2 has m nodes, so m time complexity to traverse it. And for each and every node of tree 1, you are traversing the whole level up to kth level, right? Using BFS. And as you are traversing up to kth level, what I can think that at max, how many nodes will be possible up to kth level? That we don't know. The maximum nodes that are possible up to kth level is n. N is tree 1, right? So for 0th node, for node 0, you are traversing each and every node of tree 1. So that is coming from this, traversing each and every node of tree 1, and this is for traversing each and every node of tree 1 and contributing to the array. And now you need to traverse each and every node of tree 2 to find the golden node. What is the golden node? The node that has maximum number of target nodes at a distance of k minus 1 from that node. So let's take it as m, because we are going to traverse each and every node. And for each and every node of tree 2, we are going to traverse k minus 1th level. K minus 1th level can be maximum of m, can consist all the nodes of T1, so m. But if we go by this approach, we are for this one it is done. For tree 2, we are connecting a node to, we are finding the golden node, that is we are traversing every, and for each and every m, right? Okay, so the time complexity is n squared into m squared. Now let's check the constraints. It will run or not in these constraints. So if I talk about the constraints, n is 10 to the power 3, n is 10 to the power 3, m is up to 10 to the power 3, so 10 to the power 6 into 10 to the power 6, that will be 10 to the power 12. But we know that we should have a time complexity that is lesser than or equals to 10 to the power 8. So our brute force approach will not gonna work in this problem. So now we have to think a little bit of optimal approach according to this problem. So let me rub it. Okay, we have to find a little bit of optimal approach, and that is the beauty of coding. You are always looking for something optimal, something less considering less time complexity. So let me draw the tree again. 0, 1, 2, 3, 4. This is tree 1, T1. Let's just assume it as T1. And this is 0, this is 1, 2, 3, okay, 7, and 4, 5, and 6. So we have drawn T1 and T2. Let's draw partition, because it is not very clear that which one is which tree. My drawing is so much beautiful that it is, these two trees are going to overlap and going to be one tree if I don't make the partition. So the main ambition is to 0, 1, 2, 3, 4. The main ambition is to get this array, right? The main ambition is to make the answer array, the required array that will contain this one. So can we optimize it? Like, can we make something we don't need to traverse each and every node in T1? I think it's not possible. We can't optimize it in that way. And for, let's think of tree 2. Okay, so can you see something that in tree 2, if I'm gonna find the node that has maximum number of nodes in within whose level is lesser than or equals to k minus 1, then my job is done. Then I don't have to traverse T2 again and again and again. Can you see that? Then I just need to find the maximum number of nodes that are connected at a distance of k minus 1 from T2 in T2, and just suppose the maximum number of nodes that are connected in less than k minus 1 is 3. 1 2 3 for let's 3. I will add for every number that I will get here. For connecting to tree 2, I will add 3 to this, 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 and likewise I don't have to make the traversal in tree 2 each and every time. So can we make it? Yes, we can find a node that is having the maximum number of targets in. So for this one we will do BFS, or you can do DFS first in tree 2. Okay, as I'm not talking about DFS much, let's do DFS in here. DFS, because at first we need to traverse each and every of the node. So for DFS we have considered it as m times m time complexity will be needed, and as m time complexity will be needed, find the maximum number of nodes. We again have to do BFS to find how many nodes are there in within the level k minus 1. We need to do BFS. So for BFS it will be maximum of m, but here this m square will be done once, not for each and every node of tree 1, because we are finding the golden node. Here you can easily see that as k minus 1 is equal to 2 minus 1 is equal to 1. For 0 there are 3 nodes. For 0 there are 3 nodes, 3 or 4, 1 2 3 4 5 6 7 8. Is it 8 and 9? It is 9, right? So here you can see for k minus 1, for 1 there are 1 2 3 4 nodes. For 0 it is 4. For 1 it is 1 2 3. For 1 it is 3. For 2 it is 3. For 3 it is 2. For 4 it is 4. For 5 it is 2. For 6 it is 2. So the maximum is 4 we can get. You can choose any one. You can choose either 0 or 4, any one of them, and your job will be done. So m square for this one, as you have find the what I can say, the golden node here. Now you can actually traverse each and every node of tree 1. That will cost you in time complexity. And so that will cost you around n time complexity, and for each and every node you are going to traverse up to kth level, and k can be maximum of n. So n into n. So now the time complexity is n square. Why n square? Because we are first finding the what you can say, we are first finding the golden node here. We are not finding it with the traversal of T1. So here we have done a massive reduction in time complexity. First we are finding the golden node, then we are doing this. So it is n square, and as it is n square plus m square, which will be greater, that will be. And if 10 to the power 3 square, that will be 10 to the power 6, and as 10 to the power 6 is lesser than 10 to the power 8, our code will run fine. And I will share my code in the description as well. And another thing, that it is very much important that how you will implement the BFS such that it will only traverse up to a certain level. It is very much important. For that one, you can store in the queue two things. Let's for that one you can make your own data type, which will be your own data type will be like queue entry can be your own data type, class queue entry. I am coding it in Java. Let's take one node val and one level. It shows the current level, right? And for each you will store the, like for suppose the graph is 1 2 3 4. First of all we are doing breadth first search, right? First of all it will go to 1 and level is 0, then it will go to 2 whose level is what I can say, level is 1, then it will go to 3 whose level is 1. Suppose the k is equals to 1, so the we need to travel up to level 1. So as soon as 4 is encountered with level 2, we will break the loop. That you do q is empty while q is not empty. Sorry, q is not empty. You run a loop for BFS traversal, right? In that one, you need to do this, and your job is pretty much done using a very good concept of BFS traversal. You can solve the question. We can do dry run with another. Okay, so another thing is you will be given the edges only. The edges only. So you need to make the adjacency list. Adjacency list. What is an adjacency list? Suppose I take this simple graph 1 2. For 0, what are its neighbors? Its neighbor is 1 and 2. For 1, its neighbor is 0. For 2, its neighbor is 0. So this is the adjacency list of this graph. So in adjacency list, for each index, we store its respective neighbors, and we often use adjacency list rather than the adjacency matrix, because adjacency matrix take a lot of space, and adjacency list is pretty much space efficient, and we are often comfortable to do BFS and DFS, both the algorithms, with adjacency list. So you need to convert the edges 1 and edges 2, both the array, to adjacency list, and you're pretty much done. So let's dry run. So now let's dry run with the question. So for tree 1, it is 0 1 2 3 4, and for tree 1 it is like this, and for tree 2 it is 0 1 2 3. So the value of k is equals to 1. We will return this array that we are making here, 0 1 2 3 4. We are returning this array that I have made here. So for k is equals to 1, how many nodes will be the target node of 0? First of all, find the golden node here. So k is equals to 1. If I will take a edge from this node to any node in tree 2, then for if I will calculate the maximum number of nodes from tree 2, then one edge will be calculated as this one. So for k minus 1, my number of edges, the number of nodes up to the level should be 0. So up to 0 level, so 0 level it is 1. For 0 it also 1, 1, 1. So the maximum is 1. So you can connect it to any of the edge. So I have got the maximum number of nodes connected from the golden node of tree 2 as 1. So for 0, how many nodes are there? For how many nodes? From 0 we can go to how many nodes such that the number of edges encountered are lesser than or equals to 1, that is lesser than or equals to k. We can go from 0 to 1, 1 edge, 0 to 2, 0 to 3, 0 to 4, and 0 to 0 obviously. So 1, 2, 3, 4, 5, 2, 3, 4, 5, 5, and plus 1 for 3, 2, that is 6. For 1, we can go 2, 2 plus 1, 3. For 2, we can check, we can have this node, and another from tree 2. So 3, likewise for 3, this node, and another from tree 2, that is 3, likewise this node, so from 4, from 4 to 4 we have encountered 0 edges, so 4 is calculated. From 4 to 0 we have encountered 1 edges, this is calculated. From 4 to 3 we have encountered 2 edges, so not kind. We don't want to calculate 3, we don't want to calculate 2, that is from 0 to 4 2 edges are encountered. So likewise we got the array that needs to be returned, and our job is done. But the coding part may look pretty much complex. I will share the code in the description.